Oh, that good, brilliant. 'Cause it's gone straight into presentation mode. Just making sure. Yes, it is. Right. Okay. Let's kick this session off. Welcome everybody to this Lunch and Learn session. I'm Darren Sharp. Currently principal engineer within Supply Chain Operations Network Rail. Also doing other things outside of Network Rail, generally sleeper related, but also track design and S&C and so on. So today we're going to give you an update on all things sleeper related, some challenges on some popular misconceptions on sleepers we use today and sleepers we will use in the future. I'm going to cover the different sleeper types and functions, some sleeper myth busting, sleeper development, serviceability, so lateral resistance testing updates as well, and just lastly a bit on CO2 reduction in sleepers. So as an overview, in Network Rail and within our network, you can see from this that our population of sleepers is around 77% concrete, 10% steel, 13% timber. The timber population is being replaced with composite sleepers. So side-cut composite sleepers are being used to replace timber aging assets as they come up for renewal or replacement. So whether some of that percentage then increases because the composites increase, that will be a thing we need to see and keep an eye on. In terms of where we use sleepers and what track category we use them in, so this is our track category matrix from 2102. It shows the speed to the side and the tonnage to the bottom. So category 1A, the top section there, predominantly concrete. Category 1, it's also concrete. Category 2, we start to mixing with some concrete, some steel and composites, and we have serviceable concrete sleepers that could be used in category 2 as well. And then the category 3 to 6, lower categories, lower speeds and tonnages, we have all, so concrete, steel, timber, composite and serviceable is used. The graph on the side shows the breakdown of the track kilometerage. So we have 31,500 kilometers of track on Network Rail, and that just shows you how much we have in 1A, 1 and 2. Quite, shows that we still have quite a lot in the lower categories from 3 to 6. The cycle of renewal does differ. So the higher category 1s and 2s, where we have a higher usage, our renewal cycle is 30, 40 years, whereas the lower categories sometimes can be 50, 60 years, depending on its use and type. So that's why we still have a lot of timber left in the track. We started to adopt a sort of system integration approach for sleepers. So for many years, sleepers have just been a lump of concrete or timber, which we've fixed fastenings to, or cast them in, or drilled them in. So more recently, we've looked at the system in terms of the rail pad, the insulators, the fastener, the sleeper system and what the sleeper system does, and the housing and the shoulder, and then also the undersleeper pad or any resilient layer we might stick onto the underside. So this shows the different external influences that we have on the system. Someone's microphone might be on. And so from maintainer to installer to all of the other environmental aspects that we consider when designing sleepers, and also setting standards and requirements. Certainly when we apply common safety method, risk evaluation, and when we look at it from that system context perspective. Functional requirements for sleepers, so broken down into these 8 functional requirements: maintaining gauge, transmitting lateral, vertical, longitudinal loads, retaining the rail laterally, maintaining inclination, and also maintaining plane, so rail to rail plane, providing lateral restraint, retaining the rail fastener, so retaining the rail fastener within it as well, and also transmitting the thermal forces and stresses from the rail into the ballast. But what else do we expect a sleeper to do? It just doesn't perform these functions. There are some functions that have been added to sleepers over the time. So some of them are carrying cables. We put cables through sleepers, around sleepers, on top of sleepers. We fix other equipment, not necessarily a primary function, but it's expected for some signaling equipment to be fixed to sleepers as well. So we have to be sort of cognizant of that. And other ways we may use a sleeper in terms of delivery, installation, And even down to a recent one is how we inspect from a plain line pattern recognition perspective. Can we actually identify any failures from cameras, from pattern recognition, from sensors, and anything that may be able to tell us how the sleeper itself is actually how its condition is being monitored. So our current range, we have two concrete sleepers. G44 is the sort of predominant one. It's the default sleeper we use in most of our track categories. Standard construction depth 200 mil, 305 kilos weight, manufactured via the carousel method and via the long line method. The photo on the right is the carousel line method. So that's used in Cemex down in Rochester. Uses a sort of 4-sleeper mold, which is then pre-tensioned through the mold, and then it's turned upside down and demolded. EG47 3R, so this is the third rail sleeper, shallower construction depth, so it's also used for shallow depth construction on structures, as well as a third rail and fourth rail for London Underground and DC lines compatibility as well. Manufactured again by both methods, by the long line method or the carousel method. Photo on the right is the long line at Doncaster. So it's a trackwork mold factory at Doncaster. So you've got the wires that go through all of the bays that are pre-tensioned, and then concrete set around it. So in the UK, we've got two methods of sleeper manufacturing. The carousel method is the more sort of common, the more modern system. Both have their different risks and different pros and cons. But having two systems is good for us. So it gives us some sort of diversity as well. Steel sleepers, easy and cost effective to install, manufactured by a steel press from a blank steel plate. Requires less ballast to support. So in terms of cost effectiveness, this track form type is a good value track form type. It does have issues with difficult to align and putting the rails in, and it does require good sound formation. If you're mixing that with poor formation or ballast that's been sort of mixed around over the years with the formation, then you're going to get problems along the line. So you need to have a good trap bed investigation to ensure you can use steel sleepers. They do corrode in highly corrosive environments, but there are solutions for this. So anti-corrosive protection can be provided, so we can make this more resilient for the future. And just in general, I think the environment is becoming more corrosive. So this would probably become something we'd look at in the future to ensure we do have sleepers with a anti-corrosive layer. Not third rail compatible for obvious reasons. And one of these sort of queries is it's restricted to 105 miles an hour, and tonnage greater than 10. And the question there is why? Why is it restricted? So there is some work being done to see if the sleepers can be used in higher track categories. Could there be a more value added proposition by using this sleeper in some of our track renewals? Certainly, if we have a good sound track bed, there's no reason why not. So those things are being challenged at the moment to give us another sort of low value unit rate for track installation. So let's go through a few sleeper myth busting. Again, this is a point of view. This is my point of view. Some of it's come from some of the testing we've done, some of the items that have come back, some queries and questions and guidance we've had to give over the years as well. So I've documented and bullet pointed a few of them. I'll go through them. They'll fly up as they go. So lateral resistance. In terms of lateral resistance performance, it's mainly due to sleeper weight. So this is incorrect. Sleeper depth and ballast contact pressure provide 60 to 70% of the sleeper's lateral resistance performance. So certainly in terms of how we've tested that, and in terms of static and not dynamic testing, we've demonstrated that is the case. Composite sleepers are the most sustainable material. So incorrect. We do have some sleepers that use non-recycled. So the recycled elements are very sustainable and very low in carbon, but we also do have some sleepers that use non-recycled. So I think when we say the word composite sleepers, people automatically assume we're talking about a sustainable material, and that's not always the case. Certainly, if you're using some virgin products in there that can have a high carbon footprint as well. So it's worth considering what is the material makeup of the composite sleeper. Steel sleepers have very low lateral stability and require additional strengthening when installed. Again, incorrect. We've actually done the testing to show that the spade end has a much higher lateral resistance than concrete. Previously, I think this is sort of a hangover of the old sort of crimp designs that were around in the 80s and 90s. In the 2000s, the steel sleeper and the spade end was introduced. And then we had a more resilient sleeper. So we know the resistance. And that's proven by our own testing and also British Steel's testing as well to sort of show that there is a high lateral resistance. Concrete sleepers are expensive. Incorrect. They're actually the cheapest sleeper on the market. This is the cheapest sleeper that we purchase. Even with an undersleeper pad, they're cheaper than most of the other sleepers that we purchase. So a box standard G44, for example, is around £100. We know concrete material prices do increase, and it's all at a different rate to other materials, so we do keep an eye on that. But in general, concrete sleepers are our cheapest sleeper we have. Concrete sleepers have the highest carbon footprint. So previously, when we looked at cement and we looked at all of the other added parts within a sleeper, so we look at steel and so on, we think to ourselves, wow, that is the highest CO2 that we have. In fact, it's not. They've reduced by 50%. We've done lots of work to reduce the sort of cement content to a low carbon alternative, and we're making them very similar to other material types. Sleeper reuse and cascading is being optimized within track renewal plans. So that is incorrect, and it's something we need to do. This is something that we need to align with the specifiers, the unit rate and budget planning teams, have a defined serviceability assessment as well, so that we can increase the reuse of sleepers. Sleepers are designed to outlive ballast, outlive rail, outlive fixings and fastenings. So we should be using or breaking that down and reusing those wherever possible. And in previous years, people did. We used to cascade timber. We have been cascading or reusing concrete sleepers, but we're not doing it to best effect. So we know we can make improvements there. A few more myth-busting points. Assembled sleepers have defined serviceability and residual life. So we don't. It's incorrect. We know that certain parts of a sleeper, so it could be the concrete, it could be the timber, but there's parts like base plates, there's parts like shoulders. If you broke down a sleeper, there's parts you could reuse, and there's parts that you could crush, there's parts that you could recycle. So we need to look at it in terms of the whole system and what parts can be reused and broken down for individual reuse. And we tend to give a sleeper a life, but there could be parts on that actually are reusable. So mixing new and old certainly isn't an issue with certain sleeper types. Corrosion protection for fast clips and clips in general provide the same life expectancy as the sleeper. So in recent terms, we've been providing sleepers with clips. That never used to happen 20, 30 years ago. The clips weren't delivered as part of the sleeper. This is now, you get a sleeper, you get a fast clip that's in the housing, it's part of the system. Nowadays, it's assumed to be part of the system and last as long as a sleeper, and they don't. They've got minimum protection to cope with a certain amount of deterioration. But by improving the corrosion protection, we can make the clip last as long. And there's other ways and means of doing that by moving to a better type of clip and also better type of corrosion protection. So it's just something to make people aware of. Certainly with our stacking of sleepers, we've seen that we are getting some corrosion on some of the clips that are being stored at our facility in Newcastle. So we need to be aware that the clip itself won't last as long as the sleeper. Steel sleepers are designed to be anti-corrosive and environmentally tested. So we don't. At the moment, we don't actually design them to be anti-corrosive, and we don't do any environmental testing on steel sleepers. We don't really do it we do it on composites. We've never done it on timber. We're starting to do it on concrete in a sense. But environmental testing is becoming more of a, I guess, more of a requirement as we're understanding the environment better and the changes to the environment as well. So some of this needs to apply to steel sleepers to make sure we can get a sleeper that's sort of fit and sort of climate resilient as well. Concrete sleepers are designed as a fully integrated system. Currently not. You've got several subsystems that make up part of it. You've got the shoulder, the pad, the clip, the undersleeper pad, the sleeper itself. Then you might want to add a lerp. Then there could be sensors. There's some base plate systems that may add in there. So you've got all of these additional items that we tend to add on, or in some case we do manufacture them with those in place. But a truly integrated design would design the parts together, design the fastening system with the sleeper and show that it's fully integrated and homologating them all in one system. So presently we have different suppliers supplying different things. So it means getting the suppliers together, getting the suppliers to talk, getting them to agree to, I guess, some of their parts might be intellectual property that they need to discuss. And they need to then design something specifically for a material or for a use or for a certain test. So there is quite a lot of integration that's needed. But we currently don't design concrete sleepers to a fully integrated system. Timber sleepers are more cost effective than composite sleepers. That's incorrect. They might be cheaper to purchase in the first instance, but they are very costly over their lifespan. So in terms of composites, generally they last twice as long as a timber sleeper. Most of the cost is the installation cost. The cost to install is around 300-400% more than the actual cost of the sleeper. So if you're going to fit once, fit correct and fit the right sleeper, which is the reason why we went down the route of changing out timber sleepers for composite sleepers. So I'm going to go over some of our development items that you've previously seen, and there's a few extra ones that have been added on since. We talked about the Lancour sleeper before. So for those that aren't aware, this is an integrated fastening pandroll fast clip sleeper system. So this is an example of where integration design has happened. Has increased lateral stability due to the sort of the vertical faces. It's a balanced sleeper. It's 60% reduction of embedded CO2. So that's compared to sort of previous examples and other designs, certainly by reducing the amount of plastic in there as well. So I think material reduction and sort of using material in the right places where you expect the sort of load to be imparted, then that's the main reason for this design. And it's also compatible with third and fourth rail conductor rail pots. Here's the design itself. So if you flip it over on the underside, you've got hollow sections where the ballast interlocks. You've got the fins for ballast interlocking as well. And you can see there the sort of fast clip housings in the sort of center rail seat section area. Still undergoing some dynamic testing and fastening tests. I'm not sure where that is. I need to speak to the project that are dealing with that. And I think a trial site is still being pursued. A trial site location, sorry. These are the two items. These are other examples of integrated composites. So these are sort of photographed that Intertrans have developed, obviously, on from then since. So we have the Voslo engineered polymer sleeper, and that has the integrated housing under development. And then we've got the SciCut integrated housing, again, both under development as well. The one on the left has the rail seat inclination cast in. And I think on the SciCut one, that's being adopted as part of the newer designs for inclination, so that can be part of the sleeper or part of the system that the rail seat integrates with. On the Voslo engineered polymer sleepers, they're made from just a bit of a background. I think we all know the SciCut sleeper. It's been around for many years, but this is a newer addition to the family of composite sleepers. It comes in a different material type. Generally, we talk about fiber sleepers or we talk about plastic sleepers. This is actually a mixture of plastic and sand, and the product is called Amalentec. It can be drilled into, so we can use standard drills to drill into the sleeper. I actually tried that myself, and you can, with a bit of weight, you can drill into the sleeper. similar to what you would do with a composite sleeper. The weight is slightly more. So if you look at the density, it's 1530 compared to sort of other composites that are sort of 700, 800, 900. So you are getting an additional weight there, which is some stability, but that comes with the sand itself. It's manufactured with 4-number reinforcing bars going through, so that provides the strength. There's different sleeper stiffnesses and strengths can be designed as part of the sort of custom requirements as well. You can see on the bottom left is a modular tie plate design, so that has 6 external bolted connections, and internally it's connected via, so you can see on this top right hand corner you've got Allen key bolts that sort of connect to the end of the reinforcing. So they're directly connected to the reinforcing bars, and then 4 internal screws fixing the plate into the bearer itself there. And on the right hand side, that's a version using the SKL clip, sort of integrated design for the SKL clip. Network Rail are also looking at how we can improve and develop designs with our existing sleepers. So we're looking at minimizing sleeper carbon content by design and manufacturing innovation. So working with our current suppliers, Cemex and Trackwork Mole, we're looking at reducing CO2. And we have done that. We've reduced it by 40% compared to 2022. We know we can go further by these designs by decreasing it another 5%. Concrete sleepers are being further engineered to reduce the weight. So we're looking at weight reduction, which obviously will reduce the cost and the material required, but also at the same time looking at improving the lateral resistance. So you can see the example on the top right there where we've got some cutouts and some tapering going on to improve the ballast pressure. It's all part of the work we've been doing with Cemex and Trackwork Mole. Other innovations such as cement alternatives, so lime, graphene as one, so concretine have cast some sleepers with Cemex to look at how graphene can reduce carbon in the additives within sleepers. So that's still early phases yet. No test sites, I think, have been agreed for that, but it's on a plan. Lower carbon steel materials, so greener steel, also recycled aggregates have been looked at, although that work at the moment has been paused because the risks we can perceive from it, but we need to understand them better. So it's a continual exploration, really, diving into what CO2 we have, and you'll see later on what that breakdown is, so you can see the parts that we can concentrate on. And supply chain operations and technical authority have also driven the utilisation of undersleeper pads. So previously, 3 or 4 years ago, around 30% of our sleepers were USP, and now the last year they've gone above 50%. I'm not sure whether it's 55, but it's certainly above 50% now. So it's increased a lot in the last 2 years. So that's by basically a better awareness and understanding, and making sure that it's by demonstrating that undersleeper pads do provide, an important function. Other items. So this isn't a Network Rail project. This is something I've been working on with a ballastless sleeper design for a project in Oslo. This is using a Rail 1 ballastless concrete bi-block sleeper and using a pandroll fastening. So this is using a common interface FCA system, which interfaces into the concrete via a steel dowel that's inserted at casting into the sleeper. And this allows flexibility of changing out the fastening system and adjusting stiffness later on as well. So you've got the 2 blocks either side connected by a girder there. The 2 small support holes here will have the feet in there so you can adjust them prior to concrete pouring. And here's the pandroll system. So it shows the FCA system. Bottom left-hand corner, you can see the screw that inserts into the sleeper with a shoulder housing, then that clamps onto the sleeper. The sleeper has a small recess for that sort of shoulder lip to position, so it has a sort of positive locating position for gauge. There's a complete assembly there, and you can see with the 11mm side post. So the FCA provides a 30mm vertical adjustment. So adjustment is quite important for certainly for ballastless systems, certainly where they have some heave and frost heave and concrete slabs moving as well. So they can have adjustment between the two. And there's also plus or minus 5mm horizontal adjustment and gauge adjustment in there as well. So it does make it a lot more adjustable in that terms. The rail pads can be adjusted for different stiffnesses. And you can also use other systems similar. Vanguard can also work with the common interface system. And there's one other system that can work with it as well. But this was chosen because in Fornebu they prefer the fast clip design to be used. It's part of what they have on their system already, so they wanted to sort of replicate that. So one of the queries we've had is about composite sleepers and their reuse. So we set out to do some assessments on how we can assess composite sleepers for serviceability. Our standard TRK 39 does have some wording in there and some clauses about how we assess for reuse. It was very, I guess, early stages when we put it in there. It was similar to how we would assess timber or concrete, but we wanted to check if it works. We wanted to do some validation of this process. We had over 500 side cut sleepers. Some of them returned due to over ordering, some from track renewals that had taken place, or from skeletized track where side cut sleepers were used 1 in 4, prior to renewal in 5 years' time. So they returned to Whitemore. We went up to Whitemore with side cut, and we looked at the sort of typical conditions that were coming back and how we can assess them for reuse. So guidance is to be drafted. It's still in draft stage at the moment. But it's to help our depot staff that do the visual inspection assessments so that they can then say, yes, we have these sleepers and they are reusable as well. So we're looking at how they can be used directly into certain track categories or reused exactly how they were intended to, by design. They won't be doing this, but if needed, holes can be resin repaired. So repair using spike fast or anything else. I think SciCut haven't got any specific resin repair, but certainly spike fast can be used for resin repairing of composite sleepers. And then it gives you that blank canvas to re-drill, because obviously you can't turn them upside down because of the dimples and so on. And there's no need really to push through the sleepers, like we used to do. In terms of serviceability of concretes, can we do more? If you look at these photos here, sort of top right, that's an example of how concrete sleepers can be delivered to us if they were just loaded into wagons directly from track. If we were actually asking or if we were receiving panels with concrete sleepers attached to the panel, then it's a lot easier for us to assess, and we can also pass those on as serviceable because they don't get damage in transit, and we can assess them easier. As soon as they get loaded into a wagon, they basically get used externally. We don't reuse them. So it's going to be an ask for us to ask our sort of track renewals working group to look at removing as much track as we can in panels so we can reuse more concrete sleepers. We're only using 7% of our total at the moment. So I think it's 21,000 serviceable concrete sleepers are being used. And they're sold internally, so they're used internally. We do sell some externally. Obviously, we can't confirm where their reuse is because that's out of our governance. But we know that 21,000 of our serviceable sleepers are used back in track, back in category 2 or below track categories. So just an update really on where we've gone with the lateral resistance testing. So following on what we've done previously when we looked at the whole range of sleepers with Southampton and also ballast types and shoulders and so on. Our next move was to look at how we can change the sleeper profile, how we can change the shape, and what profiles would help us increase lateral resistance and increase that headroom for lateral resistance. So that's giving us sort of more adaptation for climate change and giving us more headroom, so we know that if rail temperatures do increase, we've got more capability within the sleeper to withstand the higher rail temperature changes coming in the years to come. So this was a graph we showed previously. It sort of showed all our different sleeper types and what the result was in testing them. One thing we found was the EG47 was very low. So it was shown to be a very low compared to a G44. So a G44 sleeper is at the top there. It gives you around sort of 12 kilonewtons, 10 to 12 kilonewtons, whereas the EG47 was sort of really low. It's only averaging at something like sort of 6 kilonewtons. So we set out to improve that. We showed that the undersleeper pad did add some value. It almost doubled the lateral resistance, which showed that USPs could provide an alternative to lateral resistance plates as well. So that was a good piece of work. But then knowing that the EG47 was lacking in its design meant that we should really do something to try and improve that. So we set out with Cemex, and we set out initially with Cemex and then followed by Trackwork Mole, using their existing molds, their existing footprint. So we're not changing the footprint, not changing the depth of the rail seat, not changing the rebar, that all stays the same, just by adding in shapes, adding in contours. We looked at how we could taper, notch, or put in certain characteristics or certain surface changes to improve and increase the surface contact of the ballast. On the EG47, so EG47, what we have now to the new one, actually had an increase of approximately 48%. So you can see we measure it at 3 mil first movement, then an average 25 to 30, then a maximum movement. And what we're now doing is totaling these, so we can see the total factor. And the new EG47 was 48.6% higher lateral resistance in all of those areas there. And we're getting up to now a G44 standard. In fact, this was better than a G44. With a USP, what actually showed here with the USP is the USP showed very little difference. The USP didn't really, if you look at the totals, there was only a 2% improvement. So it goes to show all of these changes were about the contour. We'd already, with the USP previously, we'd already got up fairly high, and we got up twice that was previously there. So it showed that the USP values were still as we thought. But by changing the shape of the sides, more than the contact surface of the underside, showed that, we're getting a lot better results from that. A few factors there. So we've got a weight saving of 4.7%, which is good. Helps us then get volume saving, cost saving from the materials such as cement and aggregate and so on. But the steel and everything else will still stay the same. G44, again, using sort of tapered design. By doing that, we can increase the downward ballast pressure. So ballast pressure by building up onto the edge of the sleeper will provide additional lateral resistance. We did find that the taper recess length, so this is the length of the recess, if it's too short, then we weren't getting ballast interlocking areas, and we weren't optimizing the interlocking, and we weren't optimizing the pressure because the sections were too short. So it's like having very fine thins. You just can't get the ballast in there, and it's not adding any value. So we found that having longer recesses allowed the ballast then to interlock in a larger area, so you can get at least sort of 5 ballast particles in there locked rather than just 1 or 2. So that was really important to get that. G44, not a big improvement. It goes to show that, G44 weight is 305 kilos. The EG47 is 280. But the fact that lateral resistance for EG47 was like half the G44 is down to the depth. And by changing on the depth, by changing the side contour from EG47, it had a lot more improvements and made a lot more impact than the G44. So we've got 7.5% on the G44 by changing the sides. So you can see most of it, and this is why 60 to 70% of the lateral resistance comes from the side profiles. Sorry, not 60 to 70%, but most of the lateral resistance comes from the side profile. And by doing these designs, we sort of showed that The USP had a slight change, but not massively. Again, the side changes were predominantly the main factor for improvement there. And the weight saving on G44 is a lot bigger, so we can make a lot more saving in that as well. But having a 7.75% increase, if you were to sort of put that into sort of degrees, you could say that could be 3 or 4 degrees. So there is some work we're doing to input the test data from here into a model so that we can actually see what the CRT value increases, so we can then feed that back into our CRT calculations as well. All of those results were tabulated. We also did additional tests with other under sleeper pad manufacturers as well, just to see if we do change the sleeper pad to a different supplier, do we have a problem with meeting the lateral resistance requirements that we know an under-sleeper pad provides? And we did see some variability in that. We did some additional testing with LERPs on an EG47 as well, just to sort of just to reassure ourselves that the LERP and EG47 does meet does match to a USP with EG47 as well. And we've got various different designs from Cemex and Trackwork Mole that we're evaluating against each other to see what part of the designs work best and which ones to adopt. So next phase really is to agree an RAPW design change for G44s and EG47s, get these tested. Once we're happy and we can go for approval, then we've got a common design drawing that details the improvements that we've made with the profile changes. So here's some of the test results here with the EG47s that we did in January. And this is the changing shape of the EG47 that gave us that 50% improvement. We did find on the initial ones that there was an increase in the USP at 3 mil. So there was a 60% increase for USP, but at 3 mil, so that unlocking initial movement. So it does go to show that you have got that horizontal alignment, I guess fixing of horizontal alignment and retaining horizontal alignment is there with the USP. One important part of this really, and again, myth busting warning, is that these are all static tests. They're not dynamic. It's one sleeper only. The sleeper is partially loaded, so it replicates a sleeper and rails either side and sleepers either side. So there is a load that's imparted on it. I think it's 250 kilograms. This is a repeatable test we do, so we can repeat it. So we have reproducibility and repeatability by a consistent testing type. Some sleeper track panel testing is being done and evaluated that we're working on, and this is going to hopefully happen towards the end of the year, where we can start to apply the values from single sleeper tests into sleeper track panels, but also looking at a model that helps us assess the CRT as well as part of this. So this turned into, again, some more further myth busting for sleepers, demonstrating that our new EG47 profile designs are better than the current G44. Not all USP manufacturers' designs provide the same level of lateral resistance, so there is variability there. Having too many recesses on sleepers for ballast to lock into doesn't always create a higher lateral resistance. And that's proof by testing with the different sort of pocket sizes. And you can see on the right-hand side here, you've got this larger pocket size there, which is up to about 300 mil long pocket size for the ballast to go into. Ballast pressure increase has as much effect on lateral resistance as vertical face increase. So where we have vertical faces on the end of the sleeper, we have some slants and some other faces on there. The actual ballast pressure, the build pressure of that material that's on the side there and on the recesses, it's giving us just as much as the vertical face increase. Undersleeper designs are able to achieve better lateral resistance at 3 mil initial unhooking. So that provides us with better retention of the horizontal alignment. thus reducing those misalignments and also increasing tamping intervals as well. So USPs can sort of make the track stick in its position without the need for tamping for horizontal alignment faults. Also did some work with shoulder ballast bonding. I haven't got any results here, but worked with Goldschmidt on shoulder ballast bonding tests. So that's just bonding the shoulder itself. And we actually showed that I think the maximum value was something like 45 kilonewtons. So it's 2 to 3 times higher than a lerp. So a lerp's around 15, 16, 17. So, with ballast shoulder gluing, we can get a lot better lateral resistance. Only issue being is how long will it last? We don't know how long ballast gluing or ballast bonding lasts. It all depends on the traffic over the site, who's using it, how often we tamp, and so on. We shouldn't have to tamp so often, but those things need to be sort of brought into consideration as well. We also looked to see whether the shoulder ballast bonding affects or damages the undersleeper pad, because you've got ballast. Is that right hand photo there shows the glue trickling down the edge of the sleeper, and it just affects the bottom of the sleeper corner. So if an undersleeper pad was on there, you would see some of the glue go to the corner edge of the sleeper, but it doesn't spread to the bottom. So we know that, but we can actually shoulder ballast glue where we have undersleeper pads as well. So that was quite important to do. Shoulder ballast gluing or ballast gluing the entire sleeper width might be a concern, because then you would have it on the undersleeper pad and then you would just stiffen the undersleeper pad. So that wouldn't be good practice. But in terms of just checking where we go for shoulder ballast gluing, then we know the undersleeper pad won't be affected. Gluing undersleeper pads to concrete sleepers. So working with Sycar, FFU, and other sleeper suppliers, we've been gluing USPs onto sleepers that had a low lateral resistance, and some bearers as well. And the testing's shown that we can actually achieve a similar lateral resistance to concrete by doing that as well. Some other CO2 breakdowns that we've been looking at to see where we can, improve or reduce CO2 content. So this shows on a G44 that 69% of the CO2 content is attributed to cement, and actually, which is I guess looking at the other factors as well. Certainly in terms of the shoulders. 16%, and that's the steel shoulders, the 4 steel shoulders that are introduced in G44. So we're looking at reducing those by introducing Pandrol fast clip FE, so we can reduce that even further. So that 16% become basically 8%. But it's sort of interesting to realize that only 3% of the steel is for the CO2, so the reinforcing bars that go, because they are already sourced as sort of low carbon sourced. But accelerators and plasticizers, they do make up quite a part, because they're obviously chemicals that have a high CO2 content. Limestone or aggregates or sands are very low because they're natural resources. Same as ballast, they've got very low CO2. It's the transport for those that sort of picks up on the CO2. The actual product itself is just a processing. So there's very little CO2 that goes into that. Same with an EG47, so that breaks it down. You can see how some of the numbers shift because shoulders pay more of a bigger part in the EG47. Steel is more because there's more steel in an EG47 because we've got shallower steel, so there's more reinforcing, so it's 5% on that as well. But yeah, it goes to show how those affect, how each one of those elements affects the CO2 in there. So just going on to where this has led to in terms of low carbon track, and how we've then demonstrated this through our best in class low carbon track renewals. So we went round to the routes and we found a few sites on the eastern, western and southern. Picture on the right is of Stoke Gifford, where green steel rail was delivered, and also concrete sleepers, low carbon concrete sleepers were delivered. The addition of reused blended ballast, so if we can use blended ballast as well, will give us a further reduction, and it provides a total reduction in CO2 for track construction of 50 to 55%. So we've halved the carbon in track installation. materials. Under sleeper pads, that will be a whole life saving, a small increase in carbon because it's you've got a light pad that goes on there, but in terms of whole life carbon, you've got a big certainly a big reduction in increasing the expected life as well. In terms of our legacy, where we've moved from 2022 to 2025 and where we see ourselves in 2030, showing you what part the sleeper plays in this, in part of our overall track CO2. So breaking it down, sleeper, rail and ballast. As I said before, ballast is really low. Rail is the highest, but going to green steel, and that's a sort of a stepped approach, going from sort of 20 to 40% to 50% approach. Hopefully in the future it's all green steel, but that's all dependent on use and what our customers need and want. But the offer is there. Green steel will be made available in future contracts, and we've already initiated that now. So the availability can ramp up to 2030, and like to align with our current contracts. And really, you can see there that still sleepers are still a massive part of the track construction CO2 and what it plays. But the reduction and the further reductions by 2030, you can see a small decrease from 2025. And that's by us going with the lower profile concrete sleepers and introducing around about 6% saving on those sleepers as well. 6 to 7% saving that goes into that. And shoulders, introducing sort of the Pandrol FE shoulder as well will bring us down another 1 or 2%. So it all adds up. So there you go, and that's it. So if now I can open up to questions, I'll stop sharing.
Thank you very much. You've had quite a few questions in the chat. One just that you didn't quite mention when you presented. Just conscious that not everybody might know quite what you mean when you say green steel. Can you just summarise what you mean when you say green steel?
Yeah, so green steel is green steel that's manufactured via electric arc furnace. So it uses a high percentage of recycled steel into the process. So 60, 70, 80% of it will be recycled steel going into the process. And it's using electric arc furnace because it's got a large proportion of initial steel melted down. It doesn't need to have these sort of high temperatures that you're using with oxygen furnaces or oxygen arc furnaces, standard arc furnaces that we know and love today. So some countries have adopted it. Some castings come as green steel. Some reinforcing and rebar come as green steel already. So it's becoming more popular. But yeah.
And typically, what sort of savings are associated with that? Like
65%. So green steel is 65% less CO2 than oxygen arc furnace. So it's quite a big saving.
Thank you. Couple of other questions. So when you mentioned about the hedgehog sleepers, I just wondered whether they had the same sort of ballast requirements as, say, like a typical concrete.
Yeah.
Obviously, you showed it like that they're quite, like dimension-wise, they're smaller. So obviously, I assume they take up a bit less volume. But
yes,
is that justified in the extra ballast that you'll need around them?
So ballast cost and additional ballast isn't a big cost, and it isn't a big CO2 factor. But you're right, the ballast does consume more of the sleeper because the sleeper is almost sort of embedded in the ballast, so there will be more ballast that goes onto it. You could offset that by not needing as big a shoulder that we have because the lateral resistance is very high. So there are some offsets we can show there. But the width is slightly wider at the bottom. I think it's 280, so it's slightly wider. So if you were to look at the cross-sectional area, yes, it's less, but not as much as you think because it is quite wider compared to sort of an EG47.
And because that lateral resistance is better,
yeah.
Do you need like, can you have bigger spacings with them or say similar?
Spacings, that's more about torsional resistance as well as the bearing capacity and so on. So we'd keep the spacing as it is, but that would need to be modelled.
Okay.
You need to do some
see what I mean? It's a bit of a
trade-off,
isn't it? Yeah.
It is, yeah.
Okay.
You need to do some really detailed modelling on what the optimum spacing is because you probably could go up to 700 and you could then have a saving of, 2 sleepers less per length. and that can be a unit rate saving as well. But what we don't do is we don't do accurate modeling for this. We should do. And with new sleeper types, you could do that, but often they just want to replicate the spacing that's there at the moment, and then that can come later. Prove it works, and then introduce the rest later, so you don't make too much of a change in one go.
Thank you.
It's my advice.
And then with regard to the ballastless sleepers, have you actually done any sort of trials with those, or is that just like a concept at the moment?
So they're about to be tested in a month's time, and they're going to be installed in January for the Rail One ballastless sleepers. So that they're used in your concrete track, as I said. But it's showing how we can interface with a fastening system, but also have adaptation for changing the stiffness and changing other things on top if we need to. There could be post installation, or it could be that a new fastening type has been designed and can work with that system. So it's having the adaptability for it to work.
Very much. Next one, do you expect USPs to provide the lateral resistance benefit consistently throughout the life of the product, or do you expect a drop in performance with time?
Okay, yeah, so this is a good point, actually. On the USP reduction, so we have actually extracted some of the USPs from track to see what the performance has been reduced. It's just over there next. Sorry, my dog walker's just come in. It's just over there. Come on, Lola. Dog's sleeping. Must have put her to sleep. So the USP over time, they have looked at that, and they've looked at the performance of the USP over time. But each USP supplier has different performance and different life cycle, characteristics. But it is a requirement for it to last the length of the sleeper. So if a sleeper lasts 60 years, the USP should. And that's really been enforced in our sort of recent specs to say that we don't want a USP that starts to degrade at half the rate of the sleeper. So they've got to be proven to be abrasive resistant and wear and last as long as a sleeper.
Thank you very much. There's another one from me, actually. How old typically are the composite sleepers that you're seeing come back for reuse?
Well, they've only been introduced since 2020-21, so they're still very young. So this is we're alarmed to see them coming back, but it's because they would go into sites where you want to extend the life. So for 5 years or 3 years or 2 years, or just, we've got issues we call it sort of skeletizing, where you just want to improve the gauge and fixity 1 in 4, 1 in 3. So, you've got some stability there. And some of those are coming back, but also we get the same with concrete sleepers. We see in SCO that if there's an overorder, if there's some left on the train, if the job was curtailed or cut by 50 meters or something, those sleepers come back to us. So, obviously they go back into the system. And that's what we're looking at. So they could still get damaged by transport, and they could still be that they get damaged by offloading. So we still need to make sure that they're still fit for use in doing that. But yeah, I'd say Molly only like 4 or 5 years old, these sleepers. So they're nowhere near, if they're due to last 50 years, they're nowhere near their life cycle. So we know they're pretty good, and they're good enough for new in most instances.
Thank you very much. You also mentioned that for some of these sleepers, when they're being, when it's been decided about reuse, that you can fill the holes.
Yes. Yeah.
Are there any limits then when you re-drill, or is it literally like as though that hole was never there in the first place? Like, do you have to sort of, I don't know, like
you can? Yeah, no. So that's a good point. So there's tests that have been done to re-drill holes overlapping or next to or close to. There would be a point when if you just got one big lump of resin in the center, because you've drilled it so much, but we never really get to that stage, because that would need, like, you're talking about 6 or 7 different changes or 8. So we never really get to that stage. By then, the sleeper would have been swapped out. But the tests do look at overlapping and having ones close to as well, to make sure we get the pull-out test for that.
Thank you very much. What do we need to do as an industry to maximise the benefits and output from Whitemore and similar sites?
I think so. As an industry, it's speaking with, and this is not just our delivery partners, but also with supply chain operations, making sure we get the right wagons to panel, to lift out with panels and stack with panels and bring back to Whitemore in panels, so that then we can increase reusability in concrete sleepers. Otherwise, if they continue to go into wagons, they'll just be downgraded and sold externally as farmer field fill, basically, or car park, stuff. So yeah, we need to do that. There are things we can do by design. There's other designs we could look at for reusability, for sort of circular design concrete sleepers. We've looked at some of those, but we need to have the processes in place to manage those, and we need to have the asset management side in place to manage that as well. Undersleeper pads, when a sleeper comes back, it could be that the undersleeper pad, if it's 60 years down the line, the undersleeper pad maybe has degraded, and it could be that we're selling it as a non-USP, but it has some USP performance in it as well. So there are things we need to consider. But generally, working with our installation contractors is the main one, and that's sort of a subject that we need to sort of approach within our National Track Delivery Working Group.
Thank you very much. I think we've got time for a couple more. So another one here about, so with the shape of angles on newer sleepers, has sideways motion been monitored, i.e. if they move close to the next sleeper, either side under traffic loading?
No, not yet. No. So any longitudinal movement of the sleeper, that's a panel test that's been done without ballast in, and it's been done by TU Munich and some other universities. There's also some longitudinal resistance testing being done by Southampton University to look at that effect as well, because that has effect in the sort of longitudinal and torsional resistance and the buckle restraint as well of a panel. And that work then will help us form a better model for calculating and predicting CRT and track buckling in the future, using the sort of the single sleeper test parameters and outputs and feeding them into all of the other different parameters. But there are some tools out there that look at 30 to 40 different types of parameters, inputs to model this stuff. So it's all part of that work, and we haven't got there yet, but it's work. We're starting a lateral resistance sort of working group session with Southampton in a couple of months' time, and that's where that's being discussed and working out who can do what and who can help with what testing and validation.
Thank you very much. And one more question: do you think the track renewals community are aware that loose sleeper removals are not then used as serviceable within the network?
Sorry, repeat that again. Loose sleeper renewals.
Do you think, so basically, do you think that people are actually aware that when sleepers are getting chucked into wagons loose, that they're not generally then serviceable within the network?
Yeah, no, that I don't think they are aware. Yeah, that's why I'm hoping to sort of show that when sleepers are removed loose and forked out and just thrown into wagons with ballast and other stuff, they're automatically assessed as not reusable. Yep. Because of the damage they would have had during transportation. But also, it's difficult for us to take out the sleepers and in the yard and then stack them how you would do, because they're all upside down and they're all mixed up, and it's just logistically it's really difficult to handle them. So, and unsafe as well, the safety of it, just trying to maneuver the sleepers. So having them as a panel is ideal. And all other materials, rail as well. When rail comes in, then we've got those rail sections that then can be sold off. So all these other items as well can be used and reused. So hopefully there is a better awareness now, Molly.
Well, not just a better awareness, but we're going to need quite a few more wagons if you want everybody to stop chucking all this stuff in loose.
Wagon availability is another
wagon availability will be a big one, I'm sure, if you want to change the behaviours around that. But fantastic presentation. Thank you ever so much. I'm going to close the questions there. There are quite a few in the chat that we didn't quite get around to, Darren. So if there are any that we didn't quite cover, please feel free to do so. Those of you that are still on the call, just one last very, very quick comment. So for the next Lunch and Learn on the 30th of September, we have a session on infrastructure monitoring, where we'll be talking about advancing reliability through intelligent monitoring and decision making. And as you're all on this call, I would hope you're all vaguely interested in track, or at least trying to learn a bit more about it. So why not come along to our track renewal seminar on the 5th of November at the University of Birmingham, where we'll be talking about working together to make track renewals affordable. So if you're interested in either of those, please do take a look on the website. I'll pop some links in the chat as well. For those of you who have not met me before, sorry I didn't do my introduction at the beginning. I'm now the head of technical education within the PWI. So if anybody is looking for any training within their teams, or want to discuss any ideas or any specific requirements within your projects or sites, please do reach out. I'll pop my email in the chat as well. But thank you very much, Darren. Everyone, please round of applause, and I look forward to seeing you all soon.
Thanks, Molly. Thanks all.